Alrighty, let's crack on. So today is going to be the applications of integration. We've already had a look at all of the fundamentals so far, so we're now going to look at basically how these concepts can play in with other concepts we learned before, namely the relationship between the derivative and the antiderivative. And we'll also see how we can start doing more complicated area equations, as well as finding what's referred to as the average value of a function. All of this has applications with our anti-differentiation, or more specifically, we'll typically be using definite integrals for this sort of thing. First up, what's the relationship between the derivative and the antiderivative? Well, they are basically considered opposite operations to each other. And one of the most common kinds of questions that will come up, typically in your multi-choice section, is going to be something like this example that I have up here, where you have some derivative-related information and you're trying to find an integral, or maybe the other way around, where you have integral-related information, but you have to then find your derivative. Although typically it's going to be this way around, because if you had integral information, finding the derivative is easier that way versus this way that we'll have a look at. So in this case, we're told the derivative of this function is that. With that known, try to integrate this function. Now, why does this even need to be here? Why can't we just do the integral of this? Well, the reason why we can't just do the integral of that specifically is because, at least tech-free, this is a product of terms. And in methods, we're not taught a way, there's no like product rule equivalent for integration. We've only ever learned how to do the integral of functions just themselves, the basic functions of your power functions, circular functions, whatever function type it is. We've never looked at how to handle products of terms. This is the main way by which we are able to find these integrals. It's called integration by recognition because you're using terms that you recognize in other equations and making some inferences based off of that. The questions are pretty easy to spot. You have something derivative related and you have something integral related in the same question. They all look more or less the same as the question. We can see a few examples in the textbook as well, like diff this, then hence find antidiff, diff, antidiff, f dash integral, f dash integral. You see these little patterns that emerge in there, which tells you that we're going to basically be using this two-step procedure. First step, because we know that anti-differentiation is the reversal of differentiation, the first thing that you can do is take this equation that we have and antidiff both sides of it. So basically sticking that integral symbol on both sides of that equation. This thing gets integrated, this thing gets integrated. Because they are opposites, the integral symbol and the derivative symbol are going to cancel out, leaving you with just the x sine x. And over here, well, there's not really much else to be done, at least as far as that line goes. What we'll notice is that this streak of integrals is kind of similar to this one here. We can see that we have x cos x trapped inside this integral, kind of like how we should have x cos x in an integral over here. So the goal now becomes straightforward. Rearrange this until you get the integral of x cos x on its own. So because there's a plus between these two things, we can split that integral up into two parts. Integral of sine x, integral of x cos x. These are the same thing now. So if we get this thing on its own, by subtracting integral of sine x from both sides, we now have the expression, right? We wanted to find what this is. There's an equal sign, which means that this is equal to that. We've used the equation that we have to find the integral that we otherwise could not integrate normally. We can take this a step further, of course, because the integral of sine x is a known value. If you integrate sine, you go to negative cos, which is why that negative sign disappears and becomes a positive instead. That's this little property here. And so yeah, you just take this as far as you possibly can, removing any integral signs, simplifying whatever is possible in that situation. That's how these questions go every single time. Is there anything to clarify about how that works?
Could you repeat the last step?
Last step, so from here?
Yep.
Yeah, so up until this stage, we have rearranged to get the integral of x cos x on its own, because that's what we wanted to have. But if we look at how the answer is currently written, yes, we've got one function in there, but we've got the integral of the function in there as well. Because we do know what the integral of sine x is, we should simplify things further. Integral of sine x is negative cos x, so instead of leaving this integral in our answer, we simplify things further by actually evaluating that integral. Is that the part?
Okay.
Yep.
Yep.
Cool.
Yep.
Sweet. Okay. This is more or less a kind of standalone topic, so maybe we'll practice one or two of these together before we move on to anything else. So let's see. Probably a decent one to start would be... Yeah. Let's try this log one. Okay. So we've got f of x is equal to x natural log 2x. Find derivative, hence find integral. So we want to know what's our f dash, and we want to know integral of natural log 2x. Those are the two things we want to know. One of those is going to be significantly easier to find than the other. Let me just turn the brightness up on that real quick. Cool. All right, so the easy one, or easier one to find is going to be our f dash, our derivative. How do we find the derivative of this function?
X times 1 over 2x.
Kind of. So you've mentioned there's a times between them. When we have multiplication between our functions.
So, yeah. So product rule.
Product rule, that's it. So splitting those ones up, u equals x, v equals natural log 2x. U equals, u dash equals 1, and v dash, this is a kind of chain rule. This doesn't actually end up becoming 1 over 2x. It does end up simplifying to just 1 over x. Yeah. So to recap a bit about why that's the case, you basically do your whole, this becomes your u, so u equals 2x.
I'm starving.
V of u is now natural log u. V dash now becomes 1 over u, u dash equals 2, and then finally you're putting the multiplication between the two. So 2 over u, remember when u was 2x, which is why you now get back to the 1 over x. But okay, so we got the terms that we need, finishing up the product law, just multiplying across. So x times 1 over x, so that's just 1. F dash x equals 1, and, well, natural log 2x from that cross multiply. Derivative all sorted. Nice. So that's this one done. Hence find integral of this. So for that, I'll pull up the procedure. In fact, I could even screen grab the entire example if you'd like to have a copy of that in the chat. Otherwise, it will also be on the screen. Where we're going to progress from here. We have derivative information, and we have an integral that has very similar terms in it to that derivative. Our starting point does look a little bit different to what's in the question.
We can set it equal to each other and find the integral of both sides.
Set equal to each other. Well, yes, we're integrating both sides of the derivative equation, yes. So in other words, you could go straight off of this and just say integral of this equals integral of that. Or if you wanted to, you could even use your ddx notation. So ddx of this equals that, and then integrate both sides. Either way, as long as we're aware that the integral of f dash is just f, and the integral of this, well, that's yet to be seen. Integral of 1 plus natural log 2x dx. F of x, we already know, is x natural log 2x. So we get our equation. X natural log 2x is equal to integral 1 plus natural log 2x dx. We want this one. What are we going to do to get there?
We can split up the integral into integral of 1 and integral of natural log of 2x.
That's pretty much it, yeah. For the sake of rewriting the whole thing, I'll just split them up like that. Integral of 1 plus integral of natural log 2x. Yeah, splitting them up nicely. Finally, if we want this, so we've freed it quite a bit. What we're going to do now is what?
We'll rearrange for that integral of natural log of 2x dx.
That's it, yeah. So essentially, this is the only term that's still left on that side. So we subtract integral of 1. And that's going to equal the integral that we want. Integral natural log 2x dx. One final simplification here for our answer.
Integral of 1, that would be x.
That's it. Probably want to put a plus c here just because it is the integral and not like a definite integral.
Yeah.
But yeah, x natural log 2x. Take x plus c is equal to that. So this would be your final answer. This is what you put in at the very end. They're a pretty common question type, so it's definitely worth practicing these a bunch to make sure you've got them all good. So basically, without knowing what our f dash are or whatever, essentially you're going to have some expression f dash x equals something. First step is always going to be integral of f dash equals integral of that thing. That's going to simplify to f equals integral of that thing, and all you're going to do is rearrange whatever that integral of that thing is until you find the thing that you actually want. Worth pointing out further that this thing, this final answer here, is effectively capital F of x, where little f of x would be this thing here. And the reason why I specify that is because if you have integral boundaries like that, this is the thing that you're now subbing those boundaries into. This is the antiderivative of that. So when you do your boundaries on this, if they do come up, capital F of 2, take capital F of 0, you're shoving those in here. Which, if I have a look at the textbook, it's a bit less common. We see it in 3C, we see it in 4C. Never mind. There's a bunch of them. Some of the 7s look a bit off, though. Those look corrected to decimal places. So those aren't quite the same. That's going to be a tech active one. But yeah, I guess it's about a 50-50 whether or not you'll have to shove in those boundaries. The point being that this final thing here is your capital F of x. Do we need to practice any more of these, or are we good enough with how these are going? Cool. Even if I'm in the middle of explaining this one, feel free to let me know if you want to go back. Otherwise, let's look at the next application. This is going to extend on the fact that definite integrals give us area under a curve. What they can further do is also help us finding the area bound between two curves, or technically even more if we really wanted to. But methods is going to cap out at two individual curves, and maybe you'll have some x or y boundaries of it. Like let's say, bound between these curves, but also the line x equals 5. They'll put like vertical little stoppers in there perhaps, but the actual functions involved will cap out at 2 usually. Okay, so here's the full procedure. It is effectively going to allow us to figure out any area where the curves make up some sort of shape. All right, so you can imagine like the red and the blue lines there make up the perimeter of a sort of shape. In fact, that's the first thing we're going to try and do. Identify every line or curve that exists in the picture that contributes to the perimeter of the area we're trying to solve. So if it says, broadly speaking, find area bound between G and F, and let's pretend we didn't have this picture, bound between functions just means you're going to plot that on your graph, whether it's tech-free or tech-active, and figure out where do those lines intersect in such a way where you create a closed shape. So there is no bound area out here because there's no closed shape. Same thing over here. Even though there is an intersection here, right, there's nothing actually bounding it out here, anything like that. We only create a closed shape specifically in there. So when it says find area bound, and assuming we didn't have this picture for reference, you could create this because we're referring to specifically where do we get that closed shape. Part of that is getting you to solve step 1 here, which is identifying what curves are there. Cool. Next, we want to find the endpoints of the bound area, specifically the horizontal distance that it's going to cover, the domain, you can think of it as. Most of the time, that's just going to be where the functions intersect each other. So for instance, you can see horizontally speaking, it'll cover that sort of domain there. All right, this is as far out left as it goes. This is as far out right as it goes. And sure enough, both of those are intersections. So because they are intersections, we solve those like we solve any function intersections. Make the functions equal to each other and solve for x. Quadratic equals linear. Quadratic equals linear. This was a CAS question, so, just CAS solve it and you're totally fine. These are often CAS questions, at least if they the numbers are quite this big, they'll typically be CAS questions. But they have done similar, I think, from memory in tech-free, where you do bound area, but they're just not as complicated arithmetically with arithmetic because there's, as we'll see, a few more steps involved, and they don't want to give too many marks away for the same sort of concept. But okay, we've done that. We found our x solutions for that. Hence, we now know the bound area or the domain of our bound area. From here, we want to know which curve is on top and which curve is on bottom. And by this, we're simply referring to the y values of the function. So for instance, we can see over that full duration of the domain, the blue line is above the red line for the whole time. Out of the domain, yeah, red goes above blue, sure, but we don't care about out of the domain. We just care about inside that bound area specifically. So the blue linear is the roof of our shape. What we'll notice is the reason why we're going to identify what's on top and what's on bottom is because the definite integral of the top and the definite integral of the bottom we'll find are going to help us in a way. Definite integral of just a linear is going to give us all that blue area. Definite integral of the bottom is just going to give us the bit on the outside, not inclusive of anything on this inside bit here. Because remember, definite integral is always area under a curve. This is under the blue, this is under the red. What we'll notice is that the difference between them is the bit in the middle. So if you start with your big total area, your big block of blue, and you subtract your big block of red, what you're going to get left with is the bit on the inside, the bound area that you're trying to do. Which is why, when we try to do area bound between curves, we identify what's on top, what's on bottom, and do the subtraction in that order. Top, take, bottom. Because top gives you the biggest possible area, bottom gives you the remaining bits that you need to cut away. Now, obviously, evaluating this by hand would be a bit annoying. You'd be doing your, because it's top, take, bottom, you would have to create the equation, then anti-diff it, then shove in these big numbers. It'll typically be a casting for you to do here. Fair enough how that works? Is there anything to clarify about any of that? Cool. I'll grab a screenshot of that procedure and let's find one of them. Area between curves. Oh, actually, yeah, one final thing. Area between curves, what you'll notice is nowhere in this procedure do we actually care about where the graphs are positioned on our axes. These ones were already above the axes, perfectly fine. These ones dip below. Now, normally that's a bit of a worry because when you have area below the x-axis, it becomes negative. And we've already talked about how bound area want everything to be positive. It just so happens to be the case that because we're talking about things in terms of top take bottom, when you have area under the axis and you do area under top take area under bottom, you actually get the reverse effect and it does just sort of sort itself out. It does flip right back to being positive. So when you do get a question like this, you don't actually really care where it's located. If it was fully negative, fully positive, as long as you stick to top take bottom, it will resolve itself right back to being positive. This one in particular has even more simplification to be done. Like, for instance, we can see the symmetry involved, where basically all we would need to actually do would be to solve from 0 to 1 and then double it, because it is symmetrical. So you'll find that is also quite common. But even for questions like this, you can see how it's split between top and bottom, or above and below x-axis. You don't actually care. All you care about is the fact that blue is on top of red for that entire duration. So you're always just doing blue, the sine, take red, the cos. Don't have to split it up or anything like that. Okay, let's find one. Let's do question 2 here. So it's area bound by...
I've got a question.
Yeah.
So, will we get any questions that says find the area between the function and its inverse?
Yes, all the time.
Okay.
Very, very often. In fact, that's like the most common way it shows up in the actual exam, which is where, as you're probably already starting to think, you start relying on the inverse relationship where it's symmetrical about the line y equals x. So rather than actually doing top take bottom, where you're using the actual functions themselves, inverse and original, sometimes that inverse is really hard to find and use. So instead of doing that, you do top take line equals y equals x, and then double that. I'll try and find a...
Yeah, I was thinking about that.
Yeah, no, it works, and it's you do it all the time. I'll see if I can find one just for reference. I'm sure there'll be somewhere in my practice sacks. I'd be shocked if it wasn't. Well, it's not this one. I'll pull up one more of these and then maybe try one of the exams instead. This is technically it. Technically speaking, E of x is the inverse of log, and hang on, integral of log. Yeah, it is actually exactly this kind of question, because integral of log, unless I'm blanking, doesn't actually have a known integral. Its diff of log is 1 over x. So because of that, you can't really use this in a tech 3 anyway. So you now have to use the line y equals x for one of these, typically the f of x. Line y equals x does this sort of diagonal there, which gets you this part of the area, and then you double it to get that part of the area. So yeah, you can definitely do that sort of stuff. Hence find integral bound. They might even do it here as well, actually. Anyway, let's try to do this question too. Was that a question that I saw pop up, by the way? I don't think I...
No, just a thumbs up reaction to what you said before.
Yeah, easy. 5 minus x squared is the first function, and x take 1 all squared is the second function. So again, what we can see is we're trying to find the bound area between the two, but we're not necessarily given a picture to work with. Yeah?
I was just wondering how different is this, the kind of integration stuff we're doing now to what we did in 1-2?
Yeah, Unit 1
I
and
feel like it's
2...
not that different.
Yeah, Unit 1 and 2 doesn't do bound area between two curves. It'll do area under a curve, but I don't think we ever get to, in Unit 1 and 2 anyway, when you've got two or more curves to work with.
Yeah.
So all of this is now going to essentially be 3-4 specific.
Okay.
But okay, so we have these two functions here. We only have the functions, so it can be maybe a little bit challenging to see what the bound area of this might look like. As you do this more often, you'll be able to get a sense for what's on top and what's on bottom, and where the boundaries are going to be. Like, yes, it wouldn't be the end of the world to just sketch these. They're quite simple quadratics. But one of the things you can do even without sketching is notice, okay, this is a negative quadratic, it points down. This is a positive quadratic, it points up. And so the one that's pointing down is going to be on top. The one that's pointing up has got to be on bottom. That's actually fairly similar to what this would actually be. 5 take minus x would be that one, and then shifted right by 1 would be that. So in other words, you get a very rough idea of what that should look like. The bound area is going to be the bit in the middle because those curves create the perimeter of that shape. With that in mind, we should now be able to take a crack at our procedure. So we've already done step 1 there, which is then identifying what lines and curves are going to contribute. Step 2, what are we going to do from here? I've got the procedure up on screen share if you like, or also as a screenshot in the chat.
We have to find the intersections between the graphs.
Yep. So in this case, yes, definitely the intersections between them. More specifically, we want to find how far horizontally does that bound area stretch. In this case, both of them are the same thing. So yeah. Intersection between functions, how do we do that typically?
Set them equal to each other.
That's it. Yeah, nice and easy, simple. F of x equals g of x, and then solving that. So let's run through that. 5 minus x squared equal to x take 1 all squared. Yeah, probably just expanding this out. 5 minus x squared plus 1 minus 2x. So we're going to have 0 equals 2x squared minus 2x plus 1 take 5, so minus 4. Divide everything down by 2. And then solve the quadratic. You got a billion different ways you can do this. I'm noticing just by the look of the signs, a factorization approach is probably quite quick. So, you know, you've only got very quick and easy factors that you can test here, 2s and 1s, and that's about it. So a -2 and +1 are going to make up what we need there. X take 2, x plus 1. -2 times 1 gets you to -2. -2 plus 1 gets you to the -1 for that. X equals 2, x equals -1. Look back at your rough graph just to make sure that makes a little bit of sense. Obviously I drew that very, very roughly, but we would assume sort of like one positive and one negative solution, which sure enough we got. Cool. So unless I did any stupid algebra, we'll say that's going to be our domain there. That's step 2 all done. What else do we need?
We have to identify which one's on top and which one's on the bottom.
That's it.
As it's already been drawn, we can see that the upside down parabola that's going to be on top, and the normal side of parabola that's going to be the bottom.
That's it, yeah. F takes the top of the shape, and G takes the bottom of the shape. Nice. So, step 4 now becomes fairly trivial, because we're just basically putting it all together. Or at least the... Oh yeah, Taihan?
Yeah, I think for these questions, we probably wouldn't get a graph with it, right?
Well, we didn't. We made it ourselves.
Oh, okay, cool.
Yeah, so at least in this case, we didn't. We made it ourselves. I'll say it's about 50-50 whether you get a graph. Tech Active, they'll typically give you one, because that sort of leads back to our earlier conversation about the inverse being kind of complicated sometimes in Tech Active to get on your CAS. And so sketching it is,
Yeah, sorry. Yeah, I was about to ask, tech free and tech active, but yeah, that makes sense.
Yeah, Tech Active, much more likely. Tech free, you got about a 50-50 shot, maybe. But okay, so step 4, we're putting it all together now. Integral of top take bottom over the domain that we just found. So integral from, what do we have? Oh, it's right there. -1 to 2 of top. So top was F, bottom was G. So F take G. Depending on how this looks, you might want to split this up into 2 separate integrals. Like, for instance, putting, again, another integral -2 to 1, or -1 to 2, sorry, here, and evaluating them individually, and then putting them together like that afterwards. But because these functions are like each other, it should be easy enough to put them in the same thing. In fact, when you solve for the x-intercepts of them, what you'll find typically is that you'll kind of just do one take the other anyway. Like, for instance, here, when we did our arithmetic and expanded this out, this here ended up being G take F. Because we had G on this side, and we put all of F on that side. So if this is G take F, then simply putting a negative sign on this whole thing will get us back to the other way around, F take G. That's a bit more advanced to do that, but it does save you some time if you recognize, oh shit, hang on, that whole thing is G, that whole thing is G, that whole thing is F. I did have to subtract F from both sides to make it. But anyway, so we'll do it a bit more like we would usually do it to be a bit safer. So I'm going to have our f of x, so 5 take x squared. Not like that, of course. 5 take x squared minus all of g of x. So minus, oh, it's already in brackets actually. X take 1 all squared. dx. So again, expanding that out. 5 minus x squared minus x squared plus 1. Yeah, okay, I did that right. I thought I left it -1 for some reason. X squared plus 1 and then minus 2x. So it's going to be 5 take x squared, take another x squared, take 1 plus 2x minus 2x squared minus 1 plus 5 is plus 4 and plus 2x. Which, okay, let's quickly validate that this did end up looking like that. So this was plus minus minus, this is now minus plus plus. So one was the negative of the other, which is what we expected. So when you do these a lot of times, yeah, just go straight for using your logic on that one, saving yourself some time. But obviously it's going to be safer just doing the arithmetic again without without doing too many crazy shenanigans. Cool, we have our simplified function, and at this point here what we're up to is literally just a definite integral. We don't care about any of the background information. We know now that to finish this question we're just solving a definite integral. So how are we going to solve this definite integral?
Sorry, what was the question?
So we're up to the stage now where we've fully simplified everything we've got in step 4 there, finding the definite integral. We have the integral we're now trying to evaluate. My question was then, how are we going to actually evaluate this? Integral from -1 to 2 of this function. Yeah?
So -2x², that's going to be that's over -2x³ over 3.
Yes. That's it. Power goes up, and then you divide by that raised power. Nice.
Plus x².
Yes, just x², because you're dividing by that 2, cancelling that out.
Plus 4x.
Plus 4x, yeah.
Plus c is not.
Yeah, it's less required here, I would say. You could probably get away with it here, because you are immediately going to do your actual substitutions. But just for the safety of it, maybe. It's a good habit to have anyway. You don't want to have 2 rules in your head of when do I plus c and when do I not. If you always put it in there, you can't go wrong. But yeah, final step is going to be what?
Subtracting the top from the bottom.
That's
Wait,
it.
no, top minus
yeah,
bottom.
top minus bottom, yeah. I
Yeah.
gathered what you meant, I think. So what you meant there, capital F of 2 minus capital F of -1. Top one, take the bottom one. So this is just going to be arithmetic. Do you guys want me to finish the arithmetic of this sort of thing, or is that just wasting time? Let me know. I think you came off mute, but I didn't hear you say anything. Still a bit muffled there, unfortunately. I'll crank my audio a bit more. Try
Wait,
again.
can you hear me now?
Yeah, that's way better.
Oh no, I was gonna say I think it's fine.
I think it's fine. Yeah.
Yeah.
I think so too. Cool. So we just saw how to do one curve crossover, like two curves crossing over, and we have one bound area to work with. The next thing would be what happens if the curves cross over multiple times in the interval. Like if we have a look back at the screen share, we'll see that we're still just looking at 2 separate curves, right? The inverse and the original in this case, fairly common. But during the whole bound area that was suggested, it ended up looking like this. But what's top and what's bottom is going to be different depending on what subsection of the interval that you look at. So we're only going to slightly modify our procedure, which is to also identify if there are any crossover points. And essentially, all we're going to be doing is doing exactly the same procedure as before, but in 2 different stages. Because ultimately, we're always trying to do top take bottom. So if what's top and what's bottom crosses over at different intervals, we're just going to evaluate our integrals over those 2 separate domains. So do it once for this, and then add it to this one. In this case, red is above blue. In this case, blue is above red. That's literally all the difference is going to be here. Now, as for why the boundary looks like this, where do we get this random line from? This is the key wording that you'll see. So find area bound between function and the line x equals 1, or and the line y equals something. You'll find that that's the way they introduce like extra lines technically, but they don't necessarily become additional functions that you have to worry about usually. They're just kind of things that set the endpoints of your boundary, or maybe set the roof of the shape. But okay, so again, we had no picture, so we had to kind of create our own. These are fairly trivial though. Quadratic is super easy. And then because we know that this is an inverse relationship, doing the root afterwards is quite quick. What is a bit less quick is knowing that x equals 1 is is after this rather than before. So definitely when you notice that behavior, you would want to solve these ahead of time where these things cross over. That way you can get a good picture that's proper. Because, if x equals 1 was here instead, you wouldn't even have to care about the crossover. So find this first, and then you'll be able to more accurately put where that x equals 1 should be. So for the most part, this procedure is going to look quite similar. What's the endpoints, or what's the domain? Well, 0 to 1. Nice and easy. All the way horizontally across. Identify your crossover points. Well, again, make the functions equal each other. You're going to find that. You're also going to find another solution as well. Maybe the back half here. Nah, you wouldn't, because it's only a positive root. Anyway, so you find your solution there. Thus, we're now going to split it up between the x equals halves, right? So 0 to a half is going to be red over blue. Half to 1 is going to be blue over red. So we do exactly that. Evaluate these individually. And, as you can see, like each of these on their own is already fairly lengthy in the arithmetic. We didn't actually do it here, but you can imagine shoving x equals 2 and x equals negative 1 into that would have maybe taken up a full line in your notebook, and then doing it again is another line. So typically what you'll see is you do these, I've said it a couple of times, typically you could evaluate these individually on separate lines in your notebook and then add them up at the end. The disadvantage there is that you get to make less use of factorization. Whereas if you have it all in front of you at the same sort of time, you can start saying, well, okay, these actually share capital F over half. So if I find capital F over half of one of them, I can use it on the other. So there's little things like that you can consider as you start getting much more familiar with doing the arithmetic. You can start thinking, well, shit, how do I make this less of an ordeal? How can I make use of factorization? How can I make use of substitution? That sort of thing. This is only a minor sort of addition to what we've just done. So are there any clarification questions for the procedure so far? Cool. Okay, now I need to figure out how to do an example. Lucky me, they're giving us what I need, one to use. So we can see quite clearly those crossover, and we're actually just told where they cross over, so that'll save us some time for sure. Okay, so y equals cos x is the red one, and y equals sine 2x is the blue one. Beyond just where they're located, you can also tell which one's which based off of the shape of the curve itself. Sine, of course, starting at a 0, cos starting at a peak, or even just the overall condensedness, or how condensed sine 2x is. It's got half the period. These are little ways that you can identify that if it's a bit ambiguous, which curve is which. But okay, we have our crossover. We also know where they cross over as well. What's left to do? How are we going to find our area of the shaded region?
We have to find which part of it, and you have to separate it first and find which is the top curve and the bottom curve in each section.
Yep, exactly right. So obviously, because they cross over, what's top and what's bottom is going to be different depending on what domain you look at. So domain 0 to pi over 6 is going to be one of those. What's going to be top and bottom in that case? 0 to pi over 6.
Red one on top, blue on bottom.
That's it. As far as the actual curves themselves, we're going to have cos as the red and sine as the blue. So basically first integral is therefore going to be 0 pi over 6, and that's going to be, so it was cos, take the sine. We then, I should probably put my dx's in there. Cool. And then the second part of the domain, well, we could imagine that's probably just going to be the opposite. What's that one going to be?
Sine over cos.
Sine over cos, yep. And we're going to have pi over 6 to pi over 2 for that one. Integral pi over 6, pi over 2, sine take cos. Cool. So, two separate integrals to solve for. As we do definite integrals, we now need to first antidiff them, so finding what's our capital F of x. Yeah, why not? Let's give them a shot. You don't have to have these memorized, by the way. In the background I will pull up, actually I should already have one. Here's your formula sheet, if you want to refer to those. So, antidiffing that first integral. First up, antidiff of cos is going to get us what?
Negative sign.
So diff of cos will go to negative sign because you're going the other way around.
So,
yeah, cos will go to regular sign. 9x. But yeah, this is not a mistake you'll ever make in the actual thing. You'll just look at your formula sheet always, and it'll be there in the SAC or exam, Tech free or Tech active. That's the sine, and then that's the cos into the sine. Now we've got to do the antidiff of sine, which is going to get us
cos of 2x.
1 over 2.
Wait, oh yeah,
cos.
1 over 2 cos of 2x.
That's it, yeah. You identify the A comes out as a division, and sine goes to negative cos, because there's already a negative sign there. Yeah, exactly right. So 1 over 2 cos 2x. That's for that one anyway. This is literally just the opposite way around, so you could imagine it's just going to be... maybe I'll write it proper. Let's call this capital U of x. That's going to have... So it's the other way around, which means it's going to be half... Oh, actually this is going to be a bit... We can't quite do it that way, because remember that had a negative on it, which would make that negative half cos 2x. Oops. And then, now this one's going to have a minus sign on it, so it's going to be minus sign. That's me just sort of cheating things out. And then yeah, this is just going to get to the stage again, once we're doing capital F of top, take capital F bottom. Capital F pi over 6, take capital F 0, plus capital F pi over 2, take capital F pi over 6. So this one belongs to the second integral. This one belongs to the first integral. And even just trying to keep that, I'm already zoomed out as far as I can. Whoops. Even just trying to keep that on the same line is already... Now, yes, my phone is short, but even that would be like half of your page. What you'll notice is capital F of pi over 6 exists in both cases, so maybe one little thing you can do would be, rather than even doing like, instead of doing maybe this one first and then that one, you could even do each of these individually and then plug them in at the end. So like your working out could be, well, capital F of pi over 6 equals this. Capital F of 0 equals that. And then you sub it back into your final equation that you're trying to solve. So you might say something like A equals that. Once you get all these individually, you then go back to saying A equals what each of those now are. that'll be like the most straightforward way of making it as clear as possible what each thing looks like, because these do again get quite lengthy.
Can't we cancel there for 5, 6 because it seems in both?
Can you cancel it? Yeah, you can actually. Good point. So that's a positive one there, plus a negative one. Yeah, they just cancel. So realistically, this is just capital F of pi over 2 minus capital F 0. Yeah, another nice identification. That won't necessarily... Actually, will it always happen? Because the thing that's on the boundary between the two is going to be the one that's shared. So the order should always be the same. Yeah, I guess the things on the inside cancel. Oh, wait, sorry. I'm stupid. You can't do that, because these are V's, not F's. Whoops.
Oh, yeah.
Yeah, whoops. That's...
That makes sense. I was so confused.
Yeah, okay, no. Definitely, so they're not similar, but the overall principle is still probably sound in the sense that you might want to evaluate each of these on their own separate lines. It's just that this one was actually a slightly different function than that one. Whoops. Okay. Good catch. Jeez. But yeah, so maybe it won't be able to cancel things out necessarily, but definitely extracting them and evaluating them on their own should be a nice little way of doing things and keeping it simple. Cool. Okay. There's a few little minor things to also have a look at, like things that are not necessarily as obvious. Like maybe question 5 here, right? Which nominally only has one function in there, right? We're trying to find the area of this shaded region. But there's only one function in there. Kind of. Any thoughts on how we could approach something like question 5? Because if we just do the bound area, area under curve like we're used to, we would just get that top little hump bit stopping at the x-axis.
Would you like graph a line and then...
Yeah, elaborate. Sounds good.
As in like where you have the kind of color for the bottom.
Uh-huh.
But the only thing is you're just not... I don't think we would include that line because it's dotted or something like that, right?
So yes and no. Dotted typically will mean it's non-inclusive. You're right.
I think we can make an equation that's like horizontal.
Yeah.
So y equals to, in this case, negative a half.
Yeah, that'll be exactly it. That'll be your second curve, the one that is implicit in there. So yeah, that was actually really good on both of you. You both found it. Yes, dotted lines are typically considered non-inclusive. It's worth pointing out with your integration and diff, the difference between non-inclusive and, well, I guess more so integration, there's no such thing as inclusive or exclusive for definite integrals. So it does end up actually being the same thing whether you want to include it or exclude it, simply because it's a continuous quantity. So not inclusive 0, sure, but you are also including 0.0000000, however many zeros for 1. So they are effectively the same thing, inclusive or exclusive. That's good. Yep, so that's how we handle these ones, right? If you have a new ceiling that isn't otherwise specified, you can actually create a function to make it work like that. That's why, technically speaking, whenever you do your bound area of just a simple function, like just definite integral of y equals whatever, your bottom curve is y equals 0 every single time. So when you do your top take bottom, it's just the case that your bottom is 0, y equals 0, and it just disappears. So it's a neat little thing to consider there. Other than that, yeah, that's probably the most I could talk about on this. There's one final thing, final concept, which is the average value of a function. This is by far the most straightforward, one of the most straightforward things in all of calculus. if it says find the average value of a function, it is referring to doing this. So basically put, it's just solving the definite integral of whatever function is telling you to average, and then dividing by the length of the interval. So it says calculate average value, or find average value, or find the average of a function over interval. You're simply just plugging and playing directly into this equation. We've done definite integrals so many times, and this is literally just a division. So there shouldn't be anything complicated here. The only complications will be around either...
what does average mean here? Because I'm not understanding it.
Yeah, so great question. The average value, as far as graphically is concerned, is just going to be the average y value across the entire domain. So for instance, do I have a picture? It's alright, I'll make one. So we have our axis, we have a function that does all sorts of weirdness. The average y value is going to be somewhere like here, right? What's the average height of the function over whatever domain you're looking at? Now, that's as far as graphs are concerned. Average value in the context of an application question will depend on what that function is actually describing. So if we have a look at some examples here, we've got like heat equations where you're anti-diffing heat. So your average value is going to be the average heat over that time duration. Flows of water is going to be the volume of, or the average volume of water over that duration. So you will have to then reshape your interpretation of what average value is, depending on what the function's called. Yeah, Tyler?
Yeah, if we're finding the average and it doesn't have a domain, like, does it still remain true for, like, does it work without a domain?
Yeah, you'll never get one without a domain. At least I've never seen it, I don't think. So if there was no domain, does it even exist? Because if there's no domain, you assume infinite domain, or at least the maximal domain. So that would just be dividing by infinity there.
Ah, okay, I see.
Yeah.
Oh, just because I saw the questions all had a domain, so that's.
Oh yeah, yeah, for sure. Because that's where you get your A and B from here, and the integral terminals themselves. So yeah, actually you have to definitely, unless you put these as negative infinity and positive infinity, but as we probably just discussed, you'd also be dividing by infinity at the end.
Yep.
That's a weird little finding. That doesn't sound right. All functions, when averaged, become average 0. That seems off. There's probably some better explanation for that, but just a rudimentary look at the equation seems to imply that. But yeah, again, so the interpretation is going to depend on what the functions are. And often you'll find they are derivative functions that you're given. So it's the rate of these things. So when you're doing your antidiff, it may not necessarily be the average heat. It could be the average rate of heat escape, the average rate of volume escape. So that's another little nuance on it. If you have a diff equation, it's talking about the rate of something, versus if you have a regular equation, it's talking about the quantity itself. But yeah, we've done to death the arithmetic of a particular thing. Maybe one final little nuance is it might be kind of tough to do it like that every single time. Like, this was a question from an exam, multi-choice. It simply just said find the average value of this function. But there's no function there. There's no like h of x. But there is straight lines, and we could find them if we wanted to. But that'd be a bit time consuming. We do have the points to do it, absolutely. But if we just use a bit of geometry, we can actually solve it a bit easier. Because we just need to remember that this definite integral bit is just area under a curve. So this part of the thing, if we have a separate way of finding area under curve, so in other words, this little tent shape, if we can find that whole thing, well, do it that way instead. Which, of course, because this is made up of simple shapes, we can find those areas a lot easier than otherwise. Instead of having to find the equation of the lines, top take bottom, and then simplify things later, you can just find the definite integral by doing your shapes and adding them up instead, and then finally dividing by that length of the interval afterwards, which in this case spans from 1 to 11. So you get your area for 70, divide that by 10. And this is more a bit about like that.
Is the tech active soft basically all application?
Let's pull up one. Like the latter half of it, certainly. Multis are definitely not any application. Is it all application? I guess so. Yeah, it depends on how much you think is, like, what your threshold for what's an application is. So I'll pull one up and I'll give you my sort of 2 cents on what I consider application. This stuff isn't really application. You know, find stationary point, sketch graph. Like, yes, they're adding a whole bunch of different questions on top of each other that follow up, but each individual question is kind of stuff you've done in the textbook. Like, if you just saw this in the textbook, I mean, whatever, that's just a basic question. We did these recently. Sketching a polynomial, sure. Gradient table, so it is worth doing your like table approach for finding your nature of stationary points.
Wait, is a gradient table the same thing as a sine table, or am I? Okay.
Yeah, exactly right. So sine diagram typically is for like x for y values, whether they're positive or negative. Gradient table is whether the gradients are positive or negative.
Okay.
Here's that average value again. Find average value of function between that domain. Each of these are sort of little self-contained things. They don't really follow on with each other, even though they kind of do. It's more so stuff like this, where there's a bit of a story behind it. You got to do some interpretation. Those I would consider application. So that would be this question 3 here. Not really question 4. How far did I skip? This exam only had 4 questions? That seems a bit off.
Wait, so is it that section A's tech free and section B's tech active?
So you're going to have 2
aren't the
tests.
exams run on different days?
You're going to have 2 exams. What we're looking at here is the exam 2, where section A is considered multi-choice, section B is extended.
Okay,
Exam 1 has a single section, which is all tech-free.
Okay.
Cool. So yeah, this was a weird one, actually. I didn't realize it only had 4 questions. It's still the same
I think it's one of
marking
those
scheme.
ones that has like a bunch of like parts of it.
Yeah, well, we saw
like
definitely a
big
bunch of
questions.
parts for sure. How far do we get, actually? Got up to like G triple I. And that's not even considering all the double I's and triple I's in the other questions as well. So yeah, this question 4 is a chunky boy. That's 19 marks there. But I vaguely remember them being a bit longer. Oh, sorry, not longer, but with more questions. Yeah, like this one's got 5 full sections in it. But it still adds up to the same marks. Same deal. Anyway, that's about it. So if we have a look back at like the chapters that are relevant for this, 11J is going to help you with that average value stuff. The previous one is going to help us with the bound area between curves. Same with, again, before that, but without the crossover. As well as also getting these show up a lot. In fact, I'd hazard a guess I'd be able to find it in the multis if I look. Gonna be there. Oh, no. Damn, really? I've been really bad at calling shots recently, huh? Come on, tell me it's in the 2022. Let me end on a win. There. Not really. There we go. There it is. So I'll do even like weirder stuff, like also chucking in coefficients that are unknown. But it's the same thing. You can see it's diff of function equals this, solve an integral similar. Alrighty, I'll leave you to it. Take care, guys.
Thanks, Chris.
No worries.
Can you explain the trapezium thing? trapezium equation thing once more.
The trapezium, as in like this thing that I showed you, or the
No,
trapezium rule
the-
from back ago?
Like from the last class.
Yeah, sure. So, are you talking about like how the rule looks in the formula sheet, or just conceptually speaking?
Yeah, the rule.
Yeah, okay. So the subscripts basically tell you what x coordinates they're talking about. All of them start at x0. So basically, whatever's the leftmost x coordinate during your domain is going to be x0. Whatever's the rightmost is going to be xn, where n is essentially the number of shapes that you're using. So if I pull up something to have a look at for reference. Where was it? Apps of... Oh, it's in fundamentals. Yes. So if we look at like this, for instance, that would be your x0, that would be your xn. Or in other words, x0, x1, x2, x3,
Okay.
x4.
Yep.
N, number of trapeziums, so 4. And that should be all you need, because x0, x1, those are all used again in the function.
Okay.
That's all clear
Yep.
enough?
Yep.
Easy. Alright, I'll have a good one.
Okay,
Thanks for
thanks.
coming.
Have a good day.
You too. Bye.